Hello, algebra students. I'm with you this morning to go over one-to-one and inverse functions. Inverse functions are really important functions when we're working with relationships between different kinds of functions, especially exponential and log functions. To understand logarithmic functions, or log for short, we want to understand the inverse relationship that it has with exponential functions, which is going to be our topic after we cover this foundation. So first we want to start off with looking at one-to-one functions. So we're going to look at a new definition. To look at that, what we want to do is recall what the definition of a function is. Okay, and definition of function is that we can't have repeated x values paired with y's. So you can't have, I'm going to do a little summary here. X is in our domain paired with our y's, our range. Okay, really important definition that allows us to identify them and allows us to work with the properties of functions when we know they are functions. So in a nutshell, we could basically say functions must pass the vertical line test which I call VLT for short, the VLT test. Okay, so that's what a function is. So now a one-to-one function is a little stronger than that. The idea is that you can't have repeated x's or repeated y's. So it's a special type of function in which every unique x, or your independent variable, is paired with a unique y, which is your range value, a value from your range. Okay, so in other words, you can't have repeated x's or y's. Okay, that's what makes it a one-to-one function. So what we also say for a one-to-one function is that it must pass both the vertical line test and the horizontal line test, which I'll denote by HLT. So, well, how can we put this into practice and identify these through examples? So I'll give you a little example or illustration. Here's a function, and we're familiar with quadratic functions. So an example of a function would be a quadratic function. look at a nice graph here. Okay, let's say this quadratic function has the points 1, 0 for its vertex, 2, 1, and on the other side we have 0, 1. Okay, so here we have a function. We know it passes the vertical line test, which means that if we take a vertical line and we move it from left to right, it crosses the graph only once. Okay? There's no repeated x's here. So a vertical line test is passed with this quadratic function. Okay, so here's an example. Now this is a function, so note that this is not a one-to-one function. So when you look at this, we can see that it's a function, but we know it's not a one-to-one function because we have repeated y's. It fails the horizontal line test. So if we go across in the same sense of doing a vertical line, but we do a horizontal line, we go across this graph, you see that it crosses in more than one spot. So here's our horizontal line test, and we see it cross in this spot and this spot. Or in other words, you could look at the points and you could say, well, you have repeated y's right here. So this is a function that's not a one-to-one function. Okay, there's one example. And just to give you a little more background on identifying these. Let me go ahead and post another illustration. So our second illustration will be a line. We're very familiar with linear functions. So let's say I had a line that crossed with these 2 points. Here's the point 0, 2. Here's the point negative 1, 0. So I have this linear function. Okay. So here we have our function. So here I have a function, and if I look at this, I know it's a function because it passes the vertical line test, right? So the vertical line test is passed. And next we want to take a look at the horizontal line test. Let's take a look at this and ask ourselves, is this a one-to-one function? Well, does it pass the horizontal line test? And it looks like it does. If we take any horizontal line and we move it across, we'll see that it only crosses at one point. So you move any horizontal line up or down, and you will see that you only get one crossing point. So the answer is yes, it is. So linear functions, you could pretty much just say, are one-to-one functions because they're all going to have that behavior. So what we know is we also see that there's no possible way we'll have repeated y's. So to be a function, no repeated x's. To be a one-to-one, no repeated x's or y's. Okay, so those are two big examples for you to wrap your mind around what one-to-one functions are. Okay, so one thing we could kind of draw out to help you understand, if you take a look at all your different functions, there's a whole variety out there. And remember, functions are part of a larger universe called relations. Where not all relations are functions, but all functions are relations. inside this universe of functions, we have a type of function called a one-to-one function. So not all functions are one-to-one functions, and that's how you interpret that. Okay, moving on. Let me give you some examples of one-to-one functions in a non-graph form. So here's some examples of one-to-one functions. Number 1, f of x equals 2x minus 1. So based on what we just did in this illustration, you should be able to look at this and say it's a linear function. So yes, it's a one-to-one function. And some others. I'm going to go by my examples because I'll come back to these. 3 over x minus 1. Here I have a rational function that's a one-to-one function. And 3. Let's say there are some square root functions as well. F of x equals the square root of x plus 2. That's a one-to-one function. And if you draw that out, you'll have a half parabola that starts at -2, 0. And then there's many, many others. Okay. So what are not one-to-one functions? As we've seen, we had a quadratic. So number 1, f of x equals x squared minus 1. That is not a one-to-one function, as we saw in our illustration. 2, f of x equals 1 over x squared. That is not a one-to-one function, and there's several others out there. Those are just some standard examples for you to look at. Okay, so now that we know how to identify a one-to-one function, what we want to be able to do is look at some of these special properties of one-to-one functions. When we know what type it is in math, then we could apply certain rules and conditions based on its definition. So, let's look at some properties. Properties of one-to-one functions. Number 1, every one-to-one function has an inverse function. And this is really why we want to start by defining one-to-one functions, because to do inverses, we have to know that it is one-to-one to find its inverse. Otherwise, we don't have an inverse function. Okay? An inverse function, we have the notation f inverse of x for an inverse function. In other words, we could also say every one-to-one function has an inverse function, or it is invertible. Which is what it means to have a one-to-one, have an inverse function. Okay, now every one-to-one function will have an inverse, and its inverse. Okay, so every one-to-one function has an inverse, but there's a nice feature property between these two, and its inverse, f inverse of x, reflects across the line y equals x. So when you graph a one-to-one function, you graph its inverse, you'll see that there's a symmetric property of reflection there along the y equals x line. So you can see graphically how this works. Okay, very nice feature. Now another feature is that the domain of a one-to-one function becomes, or I'll just say is, the range of its inverse and the range of a one-to-one function is the domain of its inverse. Okay, and this is a really handy trick to use. So what you want to think of is the domain becomes the range, and the range becomes the domain of the other. There's a nice relationship between the original one-to-one function and its inverse. So if we do a little illustration of this, we say, here's my function, which is a one-to-one function, and here's my inverse function. So domain, again, are all the possible x's. So this domain becomes equal to the range of my inverse and the range of my function becomes equal to the domain of my inverse. So if you know the domain and range of your one-to-one function, you could just swap those and you automatically have the domain and range of your inverse. A nice little trick. Okay. Now the other thing that we know is the composition. One more property. The composition, and just remember the composition symbol is this little o of a one-to-one function and its inverse is equal to x. Always equal to that x. So, for instance, formally, we would say f of f inverse of x is equal to f inverse of f of x and that equals x. Very important. Or if we use our composition symbol, we could say f of f inverse equals x, which equals f inverse of f. And that's using our composition symbols. So if you put one inside the other, you always get an output that's x. very interesting way of testing whether two functions are inverses of each other. So let's go ahead and talk about some of these ways of finding inverses. Okay, so I think you have all the important properties that you could apply. And let's go ahead and take a look at some examples and applications. Okay, so there's certain tricks on finding inverses based on these properties. So if you ever don't understand how we arrive at some of the solutions or the tricks that we do, I always go back to some of these properties. That gives you a lot of tools in working with and manipulating functions and their inverses. Okay, so finding inverses. Finding inverses, okay. So, finding inverses. There's three main ways. I think the birds in the background are enjoying the lecture. Three main ways. Number one is via ordered pairs. What you do is you interchange X and Y. Okay. Number two is sort of a cumbersome way of doing it, but it's a great visual and understanding functions and their inverses. So graphically, and that is by reflecting points across the line y equals x. You could take your function, graph it, and then reflect it along this line y equals x, and you get your inverse function. So by reflecting points, I'll say slash the image. Okay. And number three is just algebraically, and this is the one that we count on the most, algebraically by interchanging x and y in your equation or in your function and solving. So I'm going to elaborate on some details on this one. So we're going to put some steps together there. But again, the idea is we're going to swap our x and y values in our actual function and then solve for a new y. So let's go ahead and start with our first few examples. Okay, so number one, let's find the inverses of ordered pairs. Okay, and the idea is just to interchange our x and y. So, number one, I'll say let f of x equal so here I have a set of three ordered pairs. Okay. And notice Again, we have to be aware of the fact that this must be a one-to-one function to take the inverse. So no, this is one-to-one. We'll check that. It is one-to-one, so we can legally take the inverse, find the inverse. Okay, so the inverse is then f inverse of x will equal, and all we do is swap our x and y values. We swap these. Okay. So we end up with 2, 1, 0, -1, 5, 3, and we have our inverse function. Okay. Sorry about my little lazy French braces there. They get a little squiggly as the day rolls on. That's my inverse function. And you could repeat with so many other different examples. You don't even have to have variables or ordered pairs that are numbers. Let's say in this case we let f of x equal a, b, c, d, and then let's say y, z. Okay. Then our inverse function is b, a, d, c, and z, y. So we just interchange those. All right, that's how we find it with ordered pairs. Now graphically, let's go over this quickly, but it's a very tedious, long process, but can be done. Once you do it once, of course, you'll hopefully know how to do it again. So graphically, so the first thing you do is graph your function, your one-to-one function, plot the line y equals x, and then reflect across y equals x to get f inverse of x. Okay. So f, make sure my inverse is clear, of x. Okay, so here's an example. Let's say we're given f of x equals minus 2/3 x plus 2 and we want to find f inverse graphically. Okay, so we're going to find the inverse graphically. What we want to do is, let's start with some ordered pairs. We note that again this is a one-to-one function, so this is one-to-one, that's a check. Okay, it's a linear function, so automatically it is a one-to-one function. So if I go ahead and find some convenient points to use here, I can see that my y-intercept is 0, 2. I'm going to use a point 3 for x. That cancels out with this 3. So that I have negative 2 plus 2. So at 3, I get 0. I could put a 6 in here. And then divide by 3 is 2 times negative 2 is negative 4. Plus 2 would be negative 2. So if x is 6, I get negative 2. It looks like I have enough points to get a decent graph. So this is for f of x, which I want to keep distinct from my f inverse of x, my inverse function. Okay, so I'm going to give myself some good space along the x-axis here. Okay, so I have 0, 2, 3, 0, and 6, negative 2. And I only need 2 points to make a line, but 3 is sort of our error check in case 1 point goes astray, which happens on that awkward day. Okay, so what we have here is we have 3, 0, 0, 2, and then the point 6, 0. No, not 6, 0, 6, negative 2. Okay, I might come back and change their position. So that is my function. I'm going to label it. Now, I want to draw the line y equals x because that's what I'm going to reflect everything about. So the line y equals x is 0, 0, 1, 1, negative 1, 1, negative 2, 2, 2, 2, 3, 3, 4, 4, etc. So I will move my 0, 2 point up here. Okay. So basically, our x and y coordinates are exactly the same. That's what it means to be the line y equals x, right? So we have 1, 1, 0, 0, negative 1, 1, negative 2, 2, 2, 2, 3, 3, and on. Now, what we want to do is reflect this line across this line. Okay? So what's going to happen is this 0, 2 point will become 2, 0. This 3, 0 point will become 3, 0, 3. So I'm going to cheat a little bit and use the property I know for ordered pairs, the idea that they interchange. So what happens is 0, 3, 0 becomes 0, 3, and then 0, 2 becomes 2, 0, and 6, negative 2 becomes negative 2, 6, here. For me, that's a little easier to do than trying to fold over, but you can fold over. You could fold over and you'll get that image, and that's the main idea. So this line right here is my f inverse of x line. So can you see how if you fold this image across the line y equals x, you get that image, and that's what you want. So of course, some of these can get a lot more complex, but to begin with, it's good to start with something simple like a linear function. Make sure you have that down, and then you could apply that technique to more involved functions. All right, now for our third and our most important technique, which is finding our inverses algebraically. Let's find our inverses. Algebraically. This is the most dependent method. Okay, this is when you're given. So this is the most used and apply when given your function equation. Okay, so the first step, here's our steps or our guideline. Every instructor, every textbook has their own guideline. So the ones I like to use are the following. Very first step, I'm going to write these down. I'm going to follow this from the example. Let your f of x equal y, or set. That's a better term. Set f of x equal to y. Okay. Now what you want to do in your actual equation is interchange everyone. I'm going to emphasize that word every, x with y in your function. Very important. Step number 3, and this could be tricky. You could get kind of messy algebraically. Solve for your new y. Okay. And 4, set your new y. At this point, once you've interchanged, you've got your inverse, and you're just doing the formalities. Solve for new y and set your new y equal to f inverse of x. Okay. And then 5, this is optional. Is to check. Okay. So that should be our main step. So check, in a nutshell, is does f of f inverse equal x? Okay, by using composition. Let's do an example. I'm going to do several examples, at least 2 examples. And typically the directions will be like find the inverses of the given function. And I'm going to add, if possible. So you want to make sure it's possible to do by being a one-to-one function. So number 1, let's start with, I had this up earlier, but we could go ahead and look at this one. F of x equals 2x minus 1. Okay. If you note here, this is another linear function, so we know it must have an inverse. So always do that check. So it is one-to-one. So my first step is setting this f of x equal to y. So y equals 2x minus 1. And now swapping, interchanging the x and y. So let's go ahead and do our swap. At this point, here's your new inverse function. As soon as you do that, you've created an inverse function. So this is your inverse. It's just now a matter of cleaning that up and getting it set equal to y, or f inverse of x. Okay, so now third, solve for y. Okay, so what we want to do here is go ahead and use our steps in solving for y. I'm going to then divide by 2, and I get y equals x plus 1 over 2. And my fourth step just says, now that we have our y isolated, we just go ahead and say this is my inverse function. That's my inverse function. And we could check our fifth step. Let's go ahead and do a check, because in some problems it'll ask you to verify whether 2 functions are inverses or not. So let's do a check. Let's do f of f inverse. So if I put this function into my original function, I should get x. So let's say if I have f of x equal to 2x minus 1, then f of f inverse will be f of x plus 1 over 2, which will equal 2 times x plus 1 over 2 minus 1. Okay, so I've inserted my inverse function into my original function. I'm taking the composition, and I end up with the 2's cancel, x plus 1 minus 1, which just equals x. And and that confirms that it is our inverse function. Great. Okay. Next step is to do another example. Give ourselves some room here. So you could go back through that and review that technique. It's good to start with a linear function, master that, and then move on to the trickier ones. Okay, so here's our second example, and this is f of x equals 3 over x minus 1. I had that earlier up on our examples of functions that are one-to-one. So you confirm here this is a one-to-one function. A little hard to see, but we'll be able to know whether it is one-to-one when we were to graph it. Okay. Now for the first step, what we want to do again is set this equal to 1. Then our second step is to swap x's and y's. We get x equals 3 over y minus 1. And third, we want to solve for y. So we want to find that mu y value, or we want to isolate the y term, the y variable. So in order to do that, I have to get rid of this denominator that contains the y. So I'm going to multiply both sides by y minus 1 we'll put the y minus 1 in parentheses. Okay, so that's how I'm going to eventually get to the y. So first, before I can even tackle this y, I'm using my markers. I want to get out of the denominator. Okay, by multiplying both sides by y minus 1. Excuse me. Okay, next step. When we do that, we end up with x times y minus 1 equals 3. Okay. And we have to distribute this out. Okay, these two are connected via multiplication. So I multiply everything out, and just take your time. What you want to make sure of is like multiplying everything out and then looking at what your situation is. Don't try to assume any steps in between. Just take it step by step. Now here I get my y by itself, and I can solve for it. What I want to do is get the xy term by itself. xy equals x plus 3. I'm in the midst of a rainfall of pollen. So we have xy equals x plus 3. Now, to get this y by itself, all I have to do is divide out by x. And I get y equals x plus 3 over x. Which leaves me with, I can rewrite this as x over x plus 3 over x. I can rewrite it as y equals 3 over x plus 1. Okay, it's perfectly okay to leave it in this format too. This just allows me to see transformations in my rational graph. Okay, so that's how I get my y by itself. And my last step now is just to say this y is equal to f inverse of x. So f inverse, my inverse function is now 3 over x plus 1. So that is the inverse of this function. And you can check. It's a good exercise on your own. And verify that is the case. So that was our little intro to 101 and inverse functions. And I am going to end there before I get rained down by a huge amount of pollen. And that should be sufficient for you to get started and work with some good examples and understand inverse functions before we get into exponential log functions. Thank you.